Hi, it's Mr. Mac, and we're going to learn a little bit about air resistance. As something is falling down due to gravity, it has a force downwards, which is weight, and a drag opposing that motion, which is upwards.
Welcome to Mr. Mac's Physics channel. He can explain things really well, and is a lot of fun to watch.
Air resistance applies to objects that are falling. The net force acting on an object falling freely under the influence of gravity is equal to the vector sum of its weight and the drag acting on it. This is shown by the equation F net equals Fw plus F drag, where F net is the net force, Fw is the weight, and F drag is the drag acting in the opposite direction. Now, since F equals ma, which is from Newton's second law of motion, we can substitute on the left-hand side for the net force, so ma equals Fw plus F drag. And if we rearrange that by dividing both sides by the mass, we find that Fw plus F drag all over m is equal to the acceleration. What does that mean? It means that the rate at which an object accelerates as it falls depends on its mass and on the drag due to air resistance. If air resistance is completely removed, then the acceleration of the object due to gravity is constant. Well, what formulae do we need? Before we have a look at that, have a look at the picture at the top of the screen, where you can see a split-second photo of a bullet that has hit the ground by ricocheting off at a very, very fast speed, another bullet that was dropped and landed at exactly the same time within the limits of the experiment. Now, the formula we need, we've actually looked at before. We need to resolve a velocity vector into its components. So the triangle in the top right, you can see the velocity vector v going up at an angle, and the angle is theta. And the side opposite to theta is vy, or the velocity component in the y direction. And the horizontal velocity component, vx, you can also see on the triangle. And we need just a little bit of basic trigonometry, and we can see that vx equals v cos theta. So the horizontal component of velocity is the magnitude of the velocity vector times cos of the angle. Similarly, we can see vy equals v sine theta. Now, we will need to use those formulae, and they're not on your formulae sheet, so we need to learn those too. We're fairly familiar with them already. We're going to use them quite a lot in projectile motion. What else do we need? We need to know Sx equals Vxt. We've seen this before. The displacement in the x direction equals the velocity in the x direction times time. So the time taken times the speed, if you like, will give us the distance covered. We also need to know v equals u plus at. Now, you'll notice I put subscripts there, so vy equals uy plus ayt, because acceleration is only in the vertical direction, in the y direction. So acceleration is always downwards due to gravity. So in projectile motion, when we deal with gravity, we're dealing with little g as the acceleration due to gravity, and that equals negative 9.8 meters per second squared. And it'll always be that. It's on the data sheet. We can use that in our formulas and calculations. We also need to know that up is always positive, which is why the acceleration due to gravity has a negative sign there. So down is taken as negative. We need to know the formula S equals ut plus a half at squared. And again, any formula in projectile motion that has an a in it for acceleration is always in the y direction. So that's why the subscripts. Don't be confused by the subscripts. You could learn this as simply S equals ut plus a half at squared, and that's what appears on the formulae sheet. However, always remember to add the subscripts so that you're not tempted to put in the velocity in a different direction. The u is always in the y direction for this equation. We also need to know v squared equals u squared plus 2as. And again, because there's an a in the equation, this is only in the y direction. So that's why the subscript's y. And again, the acceleration in the y direction is g, which equals negative 9.8 meters per second squared. So we're dealing with air resistance and drag. So what happens to a parachutist or a skydiver when they jump out of an aeroplane and then later open the parachute? Here's a graph with time measured in seconds on the horizontal axis and the vertical downwards velocity measured in meters per second. And you'll notice in the first 10 to 20 seconds, you can see that the parachutist is accelerating, and it gets to a point where around about 20 seconds or just after, the velocity levels out at 50 meters per second. And this is called the parachutist's terminal velocity. Now we need to be very careful. The terminal velocity is not zero, it's 50 meters per second downwards. That's moving very fast towards Earth. And the parachutist has to realize that at some point he or she needs to pull the ripcord and open the parachute. Well, that happens just after about 42 seconds, and you can see the parachute opens, causing a deceleration. It's quite a sudden deceleration. But please note also that the parachute continues to fall towards the Earth at this time a steady speed. And again, this is at a terminal velocity with the parachute open, just under 10 meters per second downwards, until there's a point where the skydiver or the parachutist can actually guide the parachute so it's no longer falling straight down, but has a bit of a horizontal velocity, which is not shown in the graph, except the last bit at about time 70 seconds, where the parachutist actually lands on the ground. And now we're ready for a worked example. This one involves a parachutist falling out of a plane and air resistance acting as drag. And here's the question. At what speed will a 70 kilogram skydiver be travelling 2 seconds after stepping out of the plane if we assume a uniform drag force of 20 newtons acts on him during this time? Well, what's the first step? It's data. And here it is. Uy, the initial velocity in the y direction, is 0. T, time, equals 2 seconds. M, mass, equals 70 kilograms. And G, from the data sheet, is negative 9.8 meters per second squared. The force due to drag given in the question is 20 newtons, and we need to find the velocity in the y direction at t equals 2 seconds. So what formula do we use? In this case, we'll start with Fw equals mg, the force due to weight equals mass times g. And we substitute. Fw equals 70 times negative 9.8, which equals negative 686 newtons. In other words, the force due to gravity or weight is always in the downwards direction. Now we need to add that to drag to find the net force acting on the skydiver. Now remember that both of these are vectors, so when we're adding force and it's got a negative, and we add force due to drag, and it's acting in an upwards direction, it's positive. So when we add them together, negative 686 plus 20 equals negative 666 newtons. So the net force is acting downwards. Now we'll substitute that into AY equals F net on M, which equals negative 666 over 70, which equals negative 9.5 meters per second squared. In other words, the skydiver is accelerating downwards with an acceleration of 9.5 meters per second squared. And we can use that acceleration to find the velocity in the y direction. And here's the formula. V equals u plus at. And again, notice the subscripts. It's always in the y direction. And we substitute. Vy equals 0, the initial velocity, minus 9.5 times 2, where it's 2 seconds. And we find that the answer is negative 19 meters per second downwards at t equals 2 seconds. So we've answered the question about the velocity or the speed of the skydiver. So we've seen something about air resistance, and particularly about an object or a parachutist falling. That motion downwards is due to the force due to gravity, which is the weight, but that's opposed by a force in an upwards direction, which is due to air resistance, which we call the force of drag. And those two vectors we add together and we find the net force acting on the object. I'm Mr. Mac. Thanks for watching.